Okay, we have here today another integral from the UNSW Integration Meet 2024, round 2, problem 3. We have the integral from 0 to pi sine cubed x over 1 plus cosine squared x dx. Okay, there was something about this one that made me want to try a bunch of things and kind of overcomplicate it, but then I really just realized that if we take sine cubed and I split this up and I write it as sine squared times sine x, then we basically have what we need here to do a u substitution using cosine x as our u, then the derivative is going to be minus sine x, so this is going to work. And also a sine squared x, I can just rewrite this as 1 minus cosine squared x. So doing it this way, I think it's going to work well for a u substitution. So after using all this to rewrite our integral, the only other thing I want to do is, like I said, the derivative of cosine x is actually going to be minus sine x. So to set this up, I'm just going to multiply in a minus right there, and we'll multiply a minus up front so I don't change it. And then next, let's just go ahead and substitute and make a little bit of space over here. So for my substitution, we're going to make u equal to cosine x. Go ahead and take a derivative. du is going to be just minus sine x dx. So then we'll just go ahead and substitute. So first, let's evaluate this at pi. So cosine of pi, that's just going to be minus 1. Plugging in 0, cosine at 0, that's going to be just 1. Then here in the numerator, this is going to become 1 minus u squared. This stuff over here is just all du. And then in the denominator, we end up with 1 plus u squared. And then from here, what I want to do is let's just flip the sign here in the numerator. So this becomes u squared minus 1. But so I don't change it, I'll bring a minus out front. But then what I can do is take this minus sign and use it to swap my bounds. And then from here, let's just notice that everything here, this is an even function just because u squared here in both cases. So what we can do is we can use the principle of even functions with finite bounds. What we can do is, because this is symmetric around the y-axis, I can update this bound to 0. I just need to bring a 2 out front. Next, I just want to swap the order here for a second. And what I can do, I can write this as u squared minus 1. But then for this minus 1, let's just change that into a plus 1. But then so we don't change it, let's subtract 2. So again, this whole thing here is minus 1. The reason I do that is just to get cancellation here with this 1 plus u squared. So what I need to do is take this minus 2 and split it off into a separate integral. So when we do that, we multiply minus 2 times minus 2. We're going to get a plus 4 in front here. And for the second integral over here, it's just going to become du over u squared plus 1. But now we can cancel both of these over here, and this first integral just becomes 1. And the second integral is real easy, but this is just going to be arctan. So let's just go ahead and integrate this. So first, this one's going to become minus 2. Integral of 1 is just u. And then here for this second, we're going to have 4. And this is just going to become arctan of u. And all of it's evaluated from 0 to 1. Now at 0, this is nothing because arctan of 0 is just 0. So all we need to do is just evaluate this at 1. And so what we're going to get is minus 2 plus 4. Arctan at 1 is going to be just pi over 4. But 4's are going to cancel. And then for my final solution, we get just pi minus 2. Okay, there you have it. Interesting problem from UNSW 2024. Thanks everyone for watching. Have a good day.